see what happens. Anyway, so let me get this fired up here and then we can get started. And I'm aware of the transition when you go from one person to another is always a difficult thing. So we'll try to make your life as painless as possible, as if that's going to happen. Okay, so we've got your syllabi in front of you. Let's turn this on, turn this off, and start getting started, shall we? Now, this is a 50-minute class. And I have to admit, I don't have many 50-minute classes anymore. I like the Tuesday, Thursday sequences because they have an hour and 15 minutes, which is brilliant because I can go on and 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 on, and I can get most of the stuff done. With 50 minutes, I'm going to run out of time, I can guarantee you. So probably starting with today's lecture. Anyway, this is part 2 of the geophysics course. You're done with Connors now as far as assessment is concerned, okay? So the rest of the course is basically my baby. At the end of the year, what will happen is he will give me grades for you guys. I will add them to the grades that you get in my component of the course, and that will be the final grade that you get. Word of warning, I tend to be more of a bastard in terms of marking things than he does, okay? Especially when it comes to tests. And if you've had me for tests before, which is most of you, you know I really do things critically as far as testing is concerned. So when it comes time for assessment, make sure you do the best job you can in the labs. That's going to be critical. And no matter what you might think about coloring, coloring is important in geophysics, at least my aspect of geophysics. So get yourself a decent set of colored pencil crayons of some sort. You are going to need them. And by the way, when the time comes that I start hearing you bitching and complaining, I've got 3 or 4 email messages from people who did this course a year or 2 ago and are now working either in geology or are doing graduate work in geophysics. All of them say the same thing. Thank you for teaching us good coloring skills. I'm not kidding, by the way, okay? Stop this. All right, so let's get started. Now, here's what we're going to be doing for today. It's going to be an easy-going lecture for the most part, at least until we get to the start of wave theory. I want to go over a little bit of the physics that are going to be necessary for my part of the course. First of all, we're going to start talking about class policy, etc., so you know where you stand in terms of this course. This is basically talking about the syllabus. And then I'll give you a pretty standard introduction to geophysics, which I'm almost certain is exactly what Connors gave you originally because I stole his slides a couple of years ago. So you'll see the same thing again. But it's important that we have a recap here so you know where we're going on this. All right, first of all, where to find me. This is not a bad semester for me, certainly not compared to the fall of 2009, which was a bitch. So you can find me in my office downstairs in room 49. Most of you have been down there at least once or twice before. You know that my office is actually in the back of my lab. So if you show up there, knock loudly and wait at least a minute for me to get to where you are, okay? Because it takes me about on a good day, if I'm waiting for you, it'll take me 30 seconds to get there. If I'm doing something on the computer, it might take me a minute to shut it down and stuff like that. All right, so my office hours, and the ones that are most important for you guys, will be just before this class from 9 to 10 o'clock. I have a break in between here, which I'll probably be kind of drinking coffee, hiding from you guys, but if you track me down, you can get me there as well, okay? I'm also taking a course of my own, an art course, so my afternoons on Monday, Wednesdays, and Friday are a little bit more difficult to track me down and all. All right, come find me if you need me. This will be particularly important when you start doing the geophysical interpretations, because a lot of the stuff you're going to be doing here is basically you're on your own. So you've got to make the interpretations, and if you have an idea, if you need some support or some input about how to do a correlation, come see me. I don't think there's anybody who's had geophysics before that's still around, which is a real issue in terms of trying to find somebody who's actually a TA with some experience in this area of things. So I think we're going to be on our own this time around, but I'll ask around and see if anybody is capable of doing that. As far as the syllabus goes, you have me now for the next, I guess it's 8-9 weeks, something like that. The actual material we're going to be covering is specified on the syllabus. This is just a portion of the syllabus. I want to let you know that we have there's some references here to chapters. If you did buy the book, and it was not required for this course, but it's a very good book, a very cheap book for what you want to get. If you're planning going into petroleum, that's an absolute requirement. Because what we're going to be doing here, at least in my part of the course, is just touching on basics. When you get to a field where you're using real geophysics, you're going to be referring to that on a regular basis. So go ahead and buy it now. If you do have it, this will give you some chapter references for what we're going to be doing here. As I said, though, you don't really need it. My part of the course is what we tried to, when we were setting this up, the history of geophysics goes back many, many years, actually. It started off with me and David Allison teaching it. Oh God, it must have been about 6 or 7 years ago, I guess was the last time that we did that together. And then once Dr. Allison got caught up in teaching all those GIS courses, it became very difficult for him to actually be able to participate in this course as well. So that's when Dr. Connors started participating. And even when Dr. Allison and I were doing this, we kind of divided it up into like the applied side of geophysics, whereby David and now Jim would use more like the hard rock side of things, the geomagnetics, etc. And I was focused primarily in on the petroleum side, interpretive side from there. Now that Dr. Connors is here, a lot of his focus is more on hydrology and near surface type of processes, whereas I still tend to focus in on the applied petroleum side. And I hate to tell you this, but this is as close to petroleum as we get in this at this university, at least for the current time. So even though there may be some overlapping topics here that you see, the stuff that I'm going to be dealing with is going to be focusing on the applications that go for petroleum. And speaking of that, once we get through the wave theory component of stuff, I'm going to give you a little bit of a background into petroleum, because as I said, this is the only opportunity we have here to really get into this. So we're going to talk about petroleum formation. We're going to be talking about some of the petrographic techniques that you use in petroleum as well. That'll be a lab that we'll be doing next week. And it's kind of off topic as far as geophysics or proper geophysics is concerned, but you have to realize that everything that you're going to do in petroleum is going to have a cause and effect type of component to it. So if you are going to be employed as a geophysicist trying to figure out what the properties of rocks are telling you about the potential for oil, you have to understand a little bit about reservoir characterization, and that requires you to understand a little bit about petrography as well. So we'll be in the microscope room for at least one lab. Then we'll get into the electric log, seismology, and sequence stratigraphy. In particular, if you are planning a career in geology, this is where you really have to be boned up on at least some of the buzz expressions, some of the terminology that is used here. Because as you'll learn, the whole idea of you working for a geology company and never seeing rocks again, so a petroleum company and seeing rocks, is a fallacy. For the most part, you will never see a rock if you're working in Houston or Dallas or Denver, because all of your experience is going to be turned to doing subsurface examination. You still have to understand rocks, and this is one of the things we hear from the petroleum companies all the time. They want people who have seen the rocks, can understand the rocks, have a physical understanding of the rocks, even though you're never going to see them again. Because if you don't understand how the rocks work, you can't look for those subtle variations. And in some cases, we're talking about a real small inflection of one of these waves, and that's where the oil is. And if you get good at identifying that, you find oil for the companies, they're going to be good to you. Very good indeed. Okay, so this is particularly important because sequence stratigraphy is where petroleum is largely gone now. I want to let you know there's a couple things here that may be good or bad for you. Starting with next week's lecture, 1 week from today, online only. Okay, I'm not going to get back from a trip I have to go on until after this class is over. So next week on Monday, you don't have to come to class, but I expect everybody to watch that lecture online. And I'll tell you right now too, I've done this for a couple of classes right now, and I am not happy with the amount of people that actually take that seriously. So you can expect some sort of a form of assessment when I get back on Wednesday based upon that lecture. In other words, if you don't watch the lecture on Monday, you walk in on Wednesday, there's going to be a quiz or something. If you don't know what was on that lecture, you're going to be toast. So you watch the lecture at home at the same time this class is, if you wish, or later on at night with a glass of wine in the bathtub if you want. Just don't put your laptop in the bathtub, it's bad. Yeah?
When will it be available?
It'll be available in the next couple of days. All right, but I wouldn't watch it until actually we've got through Wednesday's lecture, because everything follows, okay? So there's no sense of jumping the gun here a little bit. As far as assessment goes, 50-50. You know, you get your 50% from Connors, 50% from me. This is my breakdown. I'm not sure what he's doing this year. Attendance, speaking of which, where's the attendance sheet? 10% of your grade is attendance. And I will be checking, well, I guess I can't check attendance online and stuff like that, but if only 10% of the class is actually looking at the online lectures, and I get the stats for these things, by the way, then I'll be most perturbed. Your lab assignments, 50% of you graded from your lab assignments. And folks, you want to do the best job you can on that, no matter how tedious it gets, no matter how cumbersome it gets. And we're going to be laid out in this room. And in fact, we're probably going to have to spread out over a couple different rooms, because the sheets you're going to be using are like half the size of each of your tables, okay? 2 exams in this course, the midterm, which basically is like midway through my section, so 4 weeks from now, and your final exam, 20%. Okay. All right, so that's, anybody have a question about the syllabus? Pretty basic stuff, detailed materials on there and all. And expect changes. There are always changes. You'll ask, actually, one other thing too, I should point out that your last week, everything is TBA. I'm not sure what I'm going to do with that last week just yet. I have a plan, but I don't know if the plan is going to come through or not. So we'll see how it works. All right, getting started with the material for today, geophysics. This should be recap. Okay, everyone should know what this is all about. But let's just make sure we're all on the same game plan here. You use geophysics when you have no other choice, frankly. And the reason for this ultimately is going to be that geophysics is only a poor imitation of actually looking at the rocks in detail. But let's face it, if you can't get direct access to the rocks because they happen to be 25,000 feet below the surface of the Earth, what choices do you actually have, right? Geophysics also has one very good practical capability. It allows you to model over a very large area. And very large areas can be everything from the size of, say, an oil well region, like a quarter section, or it can be the size of an entire planet. What geophysics allows you to do is look for subtle changes, not so subtle changes, and broad-scale characterizations of a region. And the other thing that geophysics really works well for is if you actually know what you're looking for. And that's because you can model certain geophysical techniques to match the criteria that you are looking for. For example, if you happen to be looking for a sulfide-bearing rock in otherwise boring plain old granite, if you know the density is somewhat different with the sulfides, then you can actually model a technique where you can look for density differences or gravity differences or even electrochemical differences. And if you know exactly the parameters to look for, it takes not very much time at all to be able to actually fly over in a helicopter and find the hot spots. When I was in Australia back in the mid-1980s and early 1990s, there was a lot of real excitement over the idea of being able to use satellites, just simple Landsat imagery that had certain types of infrared cameras on them, because certain minerals gave a different infrared signal than other minerals did. So if you knew what you were looking for, you could actually take the photographs, tweak them through a remote sensing technique, color anything that had a high tin content in it blue, and all of a sudden all over Australia you saw these blues everywhere. And everyone was so excited. Actually, I wasn't excited because I thought, well, there goes my job, right? I'm not going to be a geologist if they actually don't need you. They just use a satellite and a bunch of nerds in a computer lab somewhere to look for economic deposits. And then they started sending out the ground truthers. And you know what they found? There's a lot more things that color things blue artificially than just tin deposits. And they got spiders, they got snakes, and in one case they got a bunch of old beer bottles that were lying around in a ditch somewhere. So it didn't really work. But the point is that we can actually apply and do things if we know what we're looking for. All right? And here's the thing, okay? All geophysics does is estimate what the geology is. And that's an important thing you have to realize, okay? When you get these profiles back, no matter what they are, what they're showing you is data, not geology. You have to be the one who interprets what the significance is of those data that are being produced. Everyone clear on this? And I swear to God, you can look at 2 seismic lines and they'll show exactly the same thing. One will be associated with an oil-bearing reservoir. Another will be characterized with nothing. And yet some people have the ability to, I don't know, to smell the differences between them. There are good geophysicists they're not so good geophysicists, okay? And there's no way that we can teach you to be a good geophysicist at this level. All we can do is introduce you to the techniques that are available, and then if you do decide to go in this particular field, it'll be the oil companies or the mining companies or the hydrogeology companies that will say, we're sending you off in these courses, you're going to learn to do this more effectively, okay? So this is an introduction and no more than an introduction. All right, as far as geophysics goes, again, this should be old news for you. We have two scales of geophysical analysis, small scale, and small scale from the point of view of my area would be a single oil well. And even though that oil well may be 25,000 feet deep, it's still considered to be a small scale thing, because what it's doing is receiving its signals, its input, from one point source. Okay, so these are shallow wells. Connors would talk about this in terms of like a well dealing with a shallow water aquifer as well. Then we have the large scale types of geophysical analysis. Now these can be of any scale, but we're talking primarily about the size of basins. And a basin would be something like half the size of the Gulf of Mexico. Or if you want to take it up one step larger, you can look at the entire Gulf of Mexico and consider that to be your survey area. All right, so there's no absolutes on this. There's not a certain size that tells you whether it's large scale or small scale. The main thing to note here is that you're talking about things that go from a point source to something where you're assimilating a lot more information. Now, case in point, what you're looking at here, this is a seismic line. And these are a couple wells that have been proposed, and I'll go over the symbology of this a little bit later on. But the idea now is that these have been targeted to certain depths. That's the depth they're going for here. That's the one they're going for there. And it's been interpreted. You're going to see fault lines. You're going to see different layers. These are actually paleontological layers. So they're essentially chronostratigraphy or timelines in it. And interpreting this type of thing is important. That's the type of thing that a geophysicist would do in a major oil company. A small oil company may employ somebody to look at this type of profile, but one that is only done in the vicinity of the actual well, because what you're looking for is to try and get an idea of where you are in terms of the stratigraphy, okay? And there are techniques, and we'll go into what these techniques are, that can reconstruct this, which is a seismology profile, using data from an electric well. Okay, and that's really the cool thing, where you can actually link these things from one to another, because ultimately what you want to be able to do is know where you are in the well compared to where you are in this much larger basin. And you know, the more I talk about this, the more that I see how people can do in this, it's absolutely stunning just how much information we have about the surface, below the surface. But again, you have to remember, ultimately, do you see any rocks there? Do you see anything that tells you that this rock is a sandstone and this rock is a limestone? You don't get it from this type of techniques, not directly. And there's all sorts of room to make mistakes if you're not careful on this, okay? All right, and again, this is something that Dr. Connors probably has mentioned to you already, that all geophysics does is look for anomalies. And the thing is, what you want to do is look for the anomalies that have significance to you. You want an anomaly that tells you that there's a sulfide deposit below the surface, or there's water below the surface, or there's gas sitting on top of water, or better yet, there's oil sitting on top of no water, just oil. Thousands of feet of oil. Buckets of it in this big huge cavern below the surface of the earth, just waiting for us to find. Oh, if only it was so true. And of course what you're looking at here is something that has no real significance in terms of economics. This is a gravity map of the Yucatan area, showing you very clearly the concentric shape of what is the impact site, or was the impact site that we thought took out the dinosaurs. Now, of course, it's considered not to be as likely that this did it. Something else may have done it. Isn't it amazing how ideas go around and come around and all sorts of things? So, and I want to show you this line here too, because this ultimately is what you can do. This is perhaps the best seismic line I have ever seen anywhere. I mean, this is actually 100% accurate to what you see. Here's the interpretation of what it is. There's the seismic line. And you can see the beautiful fold structures. You actually see the unconformities on top. There's several unconformities that are in here. And you can actually start identifying faults relatively easily through here too. So there's the interpreted section, including all manner of folds and faults and stuff on it. we have come a long way from the early seismic profiles that were done at the turn of the last century, where basically all you got was a line that showed you how electrical conductivity changed below the surface. When you consider that we can find something like this now and very accurately pinpoint where it is that we want to potentially drill. Now, even without having any experience in petroleum, you should be able to look at a chart like this and know that there are places where you would look immediately for the right characterization of rocks. In other words, which ones are the reservoirs. Chances are you're going to want to drill here, or here, or here, because you know the whole idea is that you drill on the core of anticlines. Truth of the matter is that we've drilled just about every potential anticline on the planet multiple times. All right? Remember, we've been doing this a long time. If you look at the number of holes that have been drilled in the Gulf of Mexico, it literally is inundated by tens of thousands of holes. So these things have all been drilled. The trick now is being able to start looking for things that have potential that nobody else has thought of before. For example, drilling down maybe right to that point right there, where you can see that it's faulted on both sides. Drilling down to there may give you just enough of a kick of a reservoir to be able to get something that's useful out of that. Okay? And that's the difference between a good geophysicist and a not so good geophysicist, is somebody who can look up there, make that interpretation out of it, and say, that's the place we want to drill. Everyone else has missed that. Okay? So being able to go from this to this is what everybody tries to do, but realistically you're limited in terms of the quality of the images you get. And like I said, this is about the best one I've ever seen. Most of the ones you're going to see don't look this good. Alright, so geophysics, again, you should have seen a chart like this with Jim. This is one of his that I stole directly. He probably doesn't even know this anymore. What I did here was I started highlighting the things in red that I will be talking about with applications to petroleum here. So, seismology. And the seismology we're going to be looking at, there's going to be multiple types of seismology, obviously, okay? And this is where we look at the way that seismic waves travel through rock. And we can use it in terms of looking at the property of rocks. That's basically how what we do in terms of understanding earthquakes go through rocks. Or we can actually generate our own shock waves and use them to resolve properties of the rock below. Electrical methods, these are essentially the electric logs or the different well logs that we have. There are dozens of them. You're going to be absolutely fascinated by the techniques that we have developed and the way we can actually analyze the hell out of a single oil well. Absolutely stunning. And we can determine just about every abstract property of the rocks that you can imagine. We can even obtain physical samples of the rocks when it's called for. And we're not talking about coring. Coring, as you'll learn, is very expensive. This is a lot easier to do. And as I said, when you look at some of the companies like Schlumberger, Dresser Atlas, or everybody's friend Halliburton, the techniques that they have actually developed to do this will knock your socks off. And you'll understand in some ways why these companies are sitting on billions of dollars, because the research involved in making these things work is about that same level. Okay? And lastly, we're going to be talking about radioactive methods. Oops, right along the bottom of the screen there. Not an awful lot of radioactivity in the petroleum industry, but there are a couple electric logs that are useful that show you the shale content, and I'm sure you've been introduced to those things already through the hydrology side of things. You also should know that there are both passive methods and non-passive methods. The passive methods are the ones that basically you just kind of fly over and see what the rocks are telling you. Methods, those are the methods where you actually just observe what the rocks are telling you. In other words, we measure the gravitational attraction of rocks. If they happen to be more dense, there'll be more gravity. If they're less dense, there'll be less gravity, etc. And by the way, this does have practical applications in geology as well, in the petroleum geology side of things, because if you're looking for potential oil-bearing rocks, you look for the low-density rocks. So you're looking for sedimentary rocks. We've basically done that for the entire planet now. So, best of my knowledge, nobody really goes using gravity to find oil deposits anymore. Okay, magnetics, where you're looking at the magnetic field. And again, the radioactivity side of things. The active methods, again, this is where we can more or less induce our own signals. In petroleum, Of course, seismology and the electrical methods are the major dominant ones. I'm not going to talk at all about electromagnetics. You've already got that, or should have, with Dr. Connor's component of it. So really, the stuff we're talking about, these three components, are a mixture of active and passive geophysical techniques. And they're good mix to more or less show you how petroleum really does work in the long run. All right, now about those, just an introduction. You've already had some experience with seismology, at least from the point of view of how we can use earthquakes. And earthquakes, the thing that earthquakes give us is a powerful seismic source, ones that are capable of traveling through the entire interior of the Earth. Now, the geophysics that we use in petroleum is significantly less impressive than that. In fact, in many cases, it just involves a device that sends out a ping, something that's not even audible at hearing range. But if you have sensitive enough instruments that are calibrated to hear that particular frequency, it is possible for them to actually make a pretty good interpretation of what's below the surface of the Earth. All right, so your first introduction to seismology, which you got in Geology 111 and a few other places before, allowed us to determine what the properties of the interior of the Earth were. You know, for example, being able to find the different states of mass that's below our feet. It also allows us to say something about the properties of the minerals. This diagram here, for example, which you probably have seen in one of your Geology 111 classes, shows you the speed at which the different types of waves are traveling. You'll notice that P and S waves all pick up speed the further they travel through the interior of the Earth, which makes sense because even if the state of the material starts to change, going from being rigid to ductile, the density increases, and seismic waves reflect the density of the material that you are traveling through. And then all of a sudden, at around 3,000 kilometers below the surface of the Earth, the S waves just suddenly drop off to zero. And of course, you know, that's what we interpret as meaning that the outer core of the Earth is actually liquid, because shear waves don't travel through liquids. That's simple, okay? And I should also point out, too, that we recognize three major types of waves that are generated by these seismic events. The P waves, everyone should be familiar with, are compression in nature. The S waves are secondary waves. They have a shear component to them. Again, that's pretty common knowledge. And then we have the long waves, which I never really talk about in my Geology 111 class. Do your instructors talk about L waves in the classes? No? Yeah, we tend to ignore them for some reason, and I don't really know why we do that, except that, I don't know, I guess we have enough on our plate already, okay? So stuff like this is common knowledge. You know all about it, or should. But here's something that may be new to you. Some of the things that are being done now with old techniques, and you know, the idea of understanding how the interior of the Earth works is old. That's well over 100 years old. I mean, we knew the Earth was zoned in the early 1900s. But what we're doing now is taking advantage of increasing levels of technology to build up much better pictures of the interior of the Earth. Like this, seismic tomography. This is cool stuff. We normally have been looking at the interior of the Earth in a passive way, okay? So if an earthquake happens here, boom. We see the earthquake waves travel all over the place. We can determine the size of the core by looking at the shadow zone for the S waves, all sorts of stuff that, like I said, we were comfortable with 15, 60 years ago. But now what we can do actually is start using our amazing range of seismographs around the world to start looking through the Earth. Instead of just seeing how the waves bounce off and getting an idea of the interior divisions, we can now observe how the waves travel through the Earth in this direction. That's where this tomography comes from. You put it together, it allows you now to start looking for differences in density laterally. And these differences in density can allow us to interpret things like temperature, state, etc. So these are some very simple diagrams that have been used now to show you differences in terms of temperature. So everything that's red is anomalously warm. I'm not sure if I'd say it's anomalously warm, but it's showing you differences in temperatures. Blues are cool and reds are warm. Yellows are the warmest of all. And you'll start to see areas below the mantle. This is the bottom of the mantle. We will never visit this area. And yet we have information about temperatures. And you can actually see things where there's plumes of cold material that some people, myself included, would interpret as chunks of lithosphere that literally have sunk through the entire mantle and are now sitting on the outside part of the outer core. All right? And I still find that absolutely fascinating. I'm frustrated beyond belief in trying to figure out why that would be the case, because lithosphere is supposed to be less dense rock, and it's traveling through rock that we know is getting more dense because we can see how the waves pick up speed, and yet here it is. It looks like it's sunk right through and is now sitting on the mantle. And the people that study this and interpret this are arguing that it's always going to be relatively cold compared to the stuff it's sinking through, and therefore more dense. Although I have significant problems with that. But ask yourself that. If you have a cold block of lithosphere composed of, one assumes, relatively low density minerals sitting at the outer core mantle interface, what's eventually going to happen to its temperature? It's going to rise like crazy. And then when it gets to the ambient temperature, where you have the same temperature of the surrounding, but you've got less dense material, what would you predict would happen to it? It will shoot to the top of the roof of the earth like a bat out of hell. One wonders if this may be an explanation where hotspots come from. All right? So there's things like this that, I mean, this is revolutionary stuff. This is stuff we could not have contemplated 5 years ago. And now we're doing it routinely. And look at this, we can get slices in terms of temperature variation. Cool stuff based upon a technique that's well over 100 years old. So you can imagine, if this is what we can do from a purely academic point of view, what the oil companies, which are sitting on more money than God, can do to try to find more resources to get even more money. And that's what's really cool about this whole thing, is that if you get into petroleum, you're sitting, in some cases, on the cutting edge of technology that will eventually filter down to everybody else. Seismic refraction, we're eventually going to get into this. This is the bread and butter of modern petroleum geology, and here's where we basically generate our own seismic waves. In the good old days, what we'd use as a shot point would be some sort of a seismic event, that type of thing, but we like to use explosives. I actually was on a shot line once, and it was cool, because the guys that handle these explosives are the strangest people you could ever imagine in your life. I mean, they should be well known to the FBI. Okay, I mean, they're weirdos. But it's cool because they get everything set up. These are all the geophones. We'll talk about the geophones a little bit later on. Had to be set up a certain way in a certain direction. And then they detonate the shot point, and then what they do is they just have a computer recording the waves, and they move on and do it again. Nowadays, the technology we've got, we don't even need explosives, which means the whole process is boring now. Now we have a little thing that just is basically a thumper, and literally it's like replacing the explosive with a guy with a hammer. Just sits there and goes bang like this, except the hammer is probably a 15-ton weight that we drop up and down on the ground. All right, so again, the whole idea now is, if you're trying to do a technique like this, you don't want to waste time. You want to make it as fast and efficient as possible. And of course, then we have this. Okay, so this is the type of thing that you guys are going to come to hate, either in this class. Actually, not in this class, because when we get to this, I'll explain this a little bit better, but I've been forced to fudge these seismic lines for reasons that I'll explain a little bit later on. You'll have a chance to interpret some real ones, but for the stuff that I really want you to be able to do, it's got to be something that's going to give you very interpretable results. But the thing to note here is that this is the type of thing you get. This particular interpretation has a fault running through here, and also has in this area a potential gas play. Okay, so, and if you're looking at this and going like, well, how do you know it's gas? Well, these are the types of things that I can give you some pointers on, but until you actually work for an oil company and talk to the people who have that touch, and they teach you in almost like an apprentice fashion, you're going to not be able to do any more of this than I would be able to. And I think it's important you realize that I've worked in the petroleum industry for a while, but I have never been able to have the experience to interpret lines like this in a useful fashion as far as the oil company is concerned. Oh, I can do the geology, but remember, they don't care about the geology. They want the revenue from this, okay? And that's where it takes a significant amount more skill. And incidentally, you're going to start learning terminology like this: acoustic impedance. Acoustics means, of course, sound waves, or in this case, seismic waves. And impedance is basically how it changes as you go through the rocks. And well logging, this is, I've had considerable more experience in interpreting logs like this. I kind of like this to a certain extent. And I'll go over some of the techniques that are used in petroleum by which you can actually make some heads and tails below the subsurface. And one of the things I want to do in the exercise you're going to get is correlation exercises, because ultimately being able to interpret one thing is fine, but being able to look at it, correlate over a larger area is also an important consideration. So those of you that thought you had to lasso your fence post diagrams in stratigraphy, think again. You're doing it again here, because that's one of the most important ways of looking at lateral changes. And the techniques that you learn in stratigraphy for sorting out the orientation of things to make them work well, they still work here. I do mine a little bit differently than Dr. Clark would do. After a while, you're going to realize that I tend to like lying down an awful lot. That's a terrible thing to admit to myself, but I tend to believe the best way of doing things is to put them on a table like this and sit down and look at them like that. That's the way I've always done this type of stuff, as you'll see. And then there's the applied geophysics, where you can actually start looking at things. And I love images like this because you're familiar with the salt domes. You know about how important the salt domes are down here, whether it's for a water source, whether it's for production of chlorine gas at Macintosh, whether they use it for storage. We're actually using these things, excavated ones, to store everything from contaminants to petroleum and matter things. What you have to realize is that, again, these things are found primarily through geophysical techniques, and these are the number of salt domes that are off the coast of Louisiana, and you can see just how amazingly large they are. So
what's the blue rectangle in the middle of all this stuff?
this under here?
Yeah.
I don't know. Obviously, it looks like something's been cut out of it, so I mean, it could be actually a fault system where the faults have kind of come out and shifted everything around. And I don't know enough about the Luan salt sources to say one way or another what this would be. So, good observation, though. That would be something, if I were a petroleum person, I would know exactly what the answer was for that and what the significance is. And with that, I have 8 minutes to go. Well, let's just get started on wave theory here a little bit, okay? And how much did Dr. Connors go into in terms of the physics of geophysics? Did he get into advanced differential equations for a three-dimensional state with the fourth dimension, not of time this time, but of spatial displacement? Good, then I'll do it. No, what I'm going to do is I'm just going to go over a little bit some of the math behind this, and you'll be very happy to know that you're not going to really need this too much. But when the lecture on Wednesday is going to be pretty hot and heavy, okay? So be sure to pay attention as much as you can. I will not ask you this stuff on any test, though. All right, it is complex stuff, but we have to make some assumptions, okay? At least as far as geophysics goes. We have to consider that the different mediums below the surface are heterogeneous, but that the heterogeneity, is that how it's pronounced? Is composed of homogeneous materials. Now, to make a long story short, what we're saying is that we assume that the stuff below the surface of the earth is layered. That we're going to have shales, we're going to have sandstones, we're going to have limestones, etc. Each one of those materials will be its own material, and it will be homogeneous. And folks, that is absolutely incorrect. But when we're interpreting things on a broad scale, especially at this level, we have to have some basic assumption somewhere. So while two shales may be completely different from one another, within that particular layer that we define as a shale, we're going to assume it's largely homogeneous as far as waves are concerned. Okay? So if it would help you to think of a layer cake of modeling clay, a lot of us do this for Geology 111. We'll have different layers of stuff, then we'll bend them around and show you how you can actually slice them in different orientations and get different things. Assume that the red clay is a different material than the yellow clay, is a different material than the green clay, but that all the green stuff is exactly the same as all the green stuff. Okay, that's what you have to assume in here. And it is, as I said, incorrect. All right, we also have to assume that when we start talking about these waves being emitted from whatever source or being received by whatever passive means of recording, that they're traveling by elastic displacement of the media. All right, now by this what I mean is that if that is your source, your point of the seismic event, that the waves are going to travel through the rock, all right, in an elastic fashion. And while that may not seem like it's all that important now, it is important because we have to assume that the energy is going to radiate in a certain fashion. All right? It's going to decrease over time. And again, everyone should realize this, that as you start off at one point, that's where the most energy is going to be, and it's going to diminish as time goes on away from that. But we have to make sure that the rocks, or at least assume that the rocks themselves are okay with this. And it's false, again, especially in the vicinity of where we are actually doing the shot or where we are actually inputting the seismic or the geophysical energy at that point. Okay, here you're basically destroying the entire media. Now this is a consideration if you're in petroleum, and one of the things that you have to be really careful about in some situations, if you drill a hole to get to an oil reserve, and then you're doing all your geophysical analysis in the vicinity of the hole, all right, you have to realize that the techniques that you're going to be using in some cases may be picking up the damage that you induced by drilling the hole in the first place. Everybody got that? So you have and you develop techniques that will give you an idea of what the rocks are like outside of the immediate vicinity. But by the same token, it's also not a bad idea to be able to observe some of the geophysical properties of the rocks in the damage zone, because that tells you again about some of the properties of the rocks. So you're going to see that even though we may have one technique, say the SP log, spontaneous potential, one of the basic ways we analyze any oil well, will have a short induction component to it and a longer induction component to it. Sometimes they go side by side. And while they may follow each other, every once in a while you get these crossovers or changes, which tells you something about the property of the rocks, which a good geophysicist would be able to interpret in some positive way, at least as far as the oil companies are concerned. All right, and lastly, I guess I'll end off on this slide, okay, and I'll let you read this on your own, but the idea is that we're talking about the waves traveling through the rocks harmonically through vibrations. And this is where you're going to start seeing some things where there's amplification changes, where there's going to be resonance components, where the waves will actually build a little higher. This is the same type of thing that happens in an earthquake, where every once in a while earthquake waves will get higher the further away they are from the epicenter. This type of thing travels through the rocks and is something we have to deal with in terms of interpretations as well. And with that, I'll end it for today, with one exception. I got to go here, okay? God, I didn't get through this lecture at all, did I? All right, your next lecture is going to be on reflections and refractions. I'm already behind as I thought it was going to be. This is physics part 2, although we're going to have to start off with the physics part 1 since I didn't get through any of it yet. But for Thursday's lab, bring a scientific calculator with you, because I want you to have at least some understanding as to how to do number crunching. Scientific calculator means you've got lns, logarithmic functions on it, and stuff like that. If you've got a computer, the computers almost always have a scientific emulating calculator on it. So.
Well, since our final
Yep.
why can't we do it during the week like
I cannot move a final exam. Your final's on Saturday. You don't like it, I suggest you do the survey from the SGA. The reason why we're having a Saturday exam in this course is because you guys got a 2-day holiday. All right. Now, if you have a personal problem with that, I can do it individually, but I am not allowed to change exams, period.
What if we all happen to have a problem with that?
Then I still have to have a Saturday exam. Sorry, dudes, that's just the way. I changed an exam once without permission. Oh, it was bad.
Oh.
What?
I'll talk to you about that. It's
No.
I have a wedding I gotta go to.
Yeah, we'll talk about it later on.